So, hello, dear student, how are you? A very good evening to all of you. So, firstly, please make sure the screen is visible to you and I'm audible to you. If this so, please write this thing in the chat box. Okay. Okay. Okay, JNV भावनगर, I got it. So, I hope कि मैं audible भी हूँगा आप सबको. The screen is visible, है ना? So, here we are with our lecture 3 on work energy and power question discussion. ठीक है. So basically, most of the concept we have covered only the, and today we also going to see some numerical from J means. And one thing that I want to tell you that only two topics are remaining. First is the potential energy concept, and second is the vertical circular motion. है ना? And yes, this is it. So today we are going to see some numerical on based on the work energy theorem, and also see some previous year numericals and help to analyze them, and then we will see that what should be a proper approach to solve a question from work energy and power. ठीक है. Got it? Let me see who is here. Lots of students are at JNV Ahmednagar, Mahanagar, Kolhapur, Ramnagara, Anand, and again Bhavnagar. So I welcome you all. Okay. So let's just start the lecture. Okay. So yeah. Before discussing any question, I want to recall some concept that I have taught you. Okay. Although we are not taking a proper theoretical lecture, it's a numerical lecture one, but I think we should know about the basic concept that should be used to solve this question. Okay. So my voice is clear to you, na, for everyone. So the very first concept that, and the most important concept of work energy and power chapter is work energy theory, work energy theorem. So what a work energy theorem is? Work energy theorem. So work energy theorem says that key work done by all the forces is equals to change in kinetic energy of that system. Got it? The few things regarding this theorem, you can apply this theorem. It is independent. It is independent of the nature of force. ठीक है? Which means कि force, if the force is conservative or non-conservative, you can apply the work energy theorem in both the cases. ठीक है? Although if you are trying to apply a mechanical energy conservation, that is only applicable for the conservative force field. ठीक है? It is not applicable for the non-conservative forces, which is friction. But if I talk about work energy theorem, you can apply it everywhere. ठीक है. So this is the tool you have to solve any numerical problem. ठीक है. So this is it. Two types of forces we have. Two types of forces. First is conservative and another one is non-conservative. ठीक है. कंजर्वेटिव फोर्स का वर्क डन is zero in a cycle. In a cyclic work, in a complete cycle, the work done by conservative force is zero, but the work done is not zero. Is not zero in case of a non-conservative force. ठीक है. If you take a body and complete a cycle, which means you have started from somewhere and you have covered some path and you have reached to the same point, then you have completed a cycle. So if this motion or this work is to be done by a conservative force field, which means if you are moving in a conservative force field, then the work done, final work done, which you will calculate is zero in this case. But if you talk about the non-conservative force field, then the work done is not zero. Okay, got it? So this is it I want to tell you now. Move on to this question. So I will give you 1 minute to solve this question. Please try to solve it and please tell me if it is possible for you to solve this question or not, so that we can further start the solving this question. Okay. In this question, a spring mass system is given. So in this given figure, a mass M resting on a smooth surface and the connected to a rigid wall by a massless spring of stiffness Q. The spring in its natural length, a constant horizontal force F, start acting on the block towards right. Find the speed of block as it moves through a distance x. Second, speed when the block is in equilibrium and the maximum extension produced by in the spring. So these three things we have to calculate. A constant force F is applied on it and this block has a mass small m. This spring has a stiffness small k and this is the rigid wall we have. Now try to solve this question. Okay, I'm giving you 1 minute. Got it? And your time starts now. So if I want to ask you one question, what do you guys think? We should improve the quality of question, or is it fine for you? Like we should include the question coming from G advance, or we should limit ourselves to the G mean quantity. So what do you say? Each and every one of you, I'm asking you. If you want that we should increase the level of question, then answer in one. Then write in the chat box. In the chat box, you will write one. And if you don't want to increase the level of question, then write two. Okay. Now it is simple for you, na? I'm waiting for your responses. Okay. And that is how we are going to make this class interesting. So JNV Ramnagara has said that we should increase the level of question. So this question is like easy for you. The question that we are discussing, it seems very easy for you, or medium, or very hard. So only one student has answered that we should increase the level of question. Okay, I'll try in the next lecture. Okay, I'll try to collect some problems from JE Advance, and then I will discuss to you. Okay. Now in this question, what is given to us? The mass of the block is given, the spring stiffness K is given, and some more information is given that the spring in its natural length means initially there is no spring force. Okay. And one thing more, a constant horizontal force, which means the force is constant. Okay. So we have to find the speed as it moves through a distance x. So what we are going to do, we are trying to draw the FBD of the system when it is at x distance, which means the spring has stretched itself as a distance of x, okay, as a length of x. So now it is in a natural length, which is L naught, let's say. But if you further see, because of the application of this constant force, there is a spring force developed, which is exactly equals to kx, because it has extended its length by x. So there is a equal and opposite reaction generated by this spring is kx, which is applied on the block. Okay. So spring want to get its natural length. So it just pull back. It just want to pull back itself. So that is why it is applying a force kx over u. Okay. Now, so in this situation, let's say the velocity or the speed of the block is v. The speed of the block is v. Okay. So what we can do, we can apply work energy theorem. Apply work energy theorem. Okay. Work energy theorem is said that net work done total is equals to change in kinetic energy delta. Now, initially the block is not moving. So the initial velocity of the block is 0. And at distance x, it has a velocity v. Now, we would talk about the work done. Here two forces are acting. One is this constant force, and second is this spring force, kx. Okay. Now, if you will see, the block is moving in this direction, in right direction. But the spring force is acting in left direction, opposite to the displacement. And this force F is exactly acting in the direction of displacement. So it has displaced to a value of x. Now you can easily set that the work done by this constant force, because force is not changing. But you cannot say that this kx is a constant force. No, because the it depends on the extension. Okay. So as much the spring is extended, the spring force changes its value. So this spring force is a variable force. So what do we have to do? We have to consider a dx length, and dx length हम consider करेंगे and we apply this force kx on that and calculate the work done for dx length, and then we integrate it. Okay, as we have done in previous questions in the previous lessons. Huh? So here work is done by spring force plus work is done by this constant force F, change in kinetic energy. Now work done by spring force is minus of, and let's say we do not write minus, it is kx dot dx. But we know that the dx is in opposite direction to the spring force. So, and this constant force exactly acting in the direction of the displacement. And because this force is constant, so you can take the entire length. Okay, entire displacement. Now this is 1 by 2 m v square minus 1 by 2 m u square. U is the initial velocity, which is 0. Okay. Now this will become minus of kx dx, because this will open as kx dx cos 180. Cos 180 is minus 1. So you can integrate it for the total value. And this will become f dot x fx 1 by 2 times m v square. If you integrate it from 0 to x, because this is the displacement of this block, so it will give you minus 1 by 2 times kx square. Okay, because x dx will become x square by 2. 1 by 2 we have taken outside, and this is kx square plus fx is equals to 1 by 2 times m v square. Now, for you guys, so if you take the value of 1 by 2 mv square in the left hand side and make it fx minus 1 by 2 times kx square, and you just divide it by m by 2 in the both sides, so you will have here v square, or here you will have 2fx by m minus 2 by 2, then 2 will cancel, kx square by m. Again, you can write it as v is equals to square root of 2fx by m minus kx square by m. So this is the velocity at, this is the velocity as it moves through a distance x. Okay, I hope you are clear with this. Now move on to the next part. We have to calculate the speed when the block is in a equilibrium position. Now, if you will see that in this block, there is a spring attached and there is a spring force is acting. Let's say the spring force I am denoting. And here is a constant force F. This force has a constant value, let's say C. But this is a variable force. When will this block come into equilibrium? Equilibrium means the net force on the system, F net of system, will be 0. Here two forces are acting on this system or this mass block M, which is F and Kx. So if F is equals to Kx, then you can say that F net on the system will become 0. Okay? Got it? So this is the condition for equilibrium. So you can write here for equilibrium, you can say this force F is exactly equals to Kx. So from here you can calculate the value of X, which is F by K. Now, what do you have to find? You have to find the speed when the block is in equilibrium. You know the speed at general position, which is x. So it is v is equals to square root of 2fx by m minus kx square by m. ठीक है. Now you put the value of x. So v is equals to v at equilibrium is equals to square root of 2 into f into what is the value of x? X is f by k into m minus k times what is the value of x square? It is f square by k square, and here in bottom side we have m. Then this power will cancel out this power. So v at equilibrium is equals to 2f square by km or mk minus f square by mk. Now this is 2 times of f square by mk. This is minus f square by mk. So we will have finally v equilibrium equals to f square by mk, or you can write it as f over square root of m. The same question is being asked in 2019 in JEE Main. Okay. So just try to remember these three things, that when a general position x is has been asked, so you have to apply this approach. Okay. Apply the work energy theorem, and calculate the work done. Just remember the spring force work done is to be calculated by the integration process because it is a variable force. But when you has been asked the velocity of equilibrium or any situation for equilibrium, so you have to just equate the forces. Okay, you just have to equate the forces. Got it? Now, is this clear to you? Now, if we will move to the next part, which is maximum extension produced in the spring. So maximum extension के लिए what do we have to do? Maximally कब extend करेगा? If this is the spring, this is mass m, then this is force F is acting. So when the value of this spring force kx will become larger than F, at that time this F is not sufficient enough to pull the block further, which means at that situation the block try to, or the spring force is dominating in nature and it pull the block backside. But just before that moment spring as it is maximum extension, है ना. ये फोर्स जो हम लगा रहे हैं दैट इज कैपिटल एफ, इस ब्लॉक को खींचती जा रही है, खींचती जा रही है. ठीक है. एंड दिस spring force is continuously increasing because of the F is equals to kx nature. It depends on the stretching. So जितनी ज्यादा स्ट्रेचिंग हो रही है उतनी ज्यादा ये स्प्रिंग फोर्स बढ़ रही है. एक टाइम ऐसा आएगा कि दिस फोर्स, स्प्रिंग फोर्स, will equate this constant force, and that is why we have kept this force as constant, this capital F. ठीक है. So at that time the spring, just after that moment, this force that is applied by us, that capital F, is not sufficient enough to pull the block further. So the spring force is dominating nature in that case, and it will pull the block back. Okay. But just before, at the equilibrium position, at F is equals to kx, F is equals to, when these forces, this spring force is greater than this F, the spring will pull it back. Okay. The spring try to pull it back. I'm not saying that spring just starting it to pull the block backside. No, because at that time the velocity at equilibrium position, block has some velocity we have seen here. This is the equilibrium velocity, and because of this velocity, the block will move further. Okay, got it? And when will the maximum extension occur? when this velocity of the block will become zero. So स्प्रिंग से एक्सटेंड किया यहाँ पे आकर के velocity zero, then it the spring will pull it back. Okay. So for maximum extension, you have to keep this in your mind. For maximum extension, for maximum extension, put speed of the block equals to zero. ठीक है. So if we put the speed, which is this, this is equals to v is equals to square root of 2fx by m minus k x square by m. So when x become x max, the maximum extension, then v will become 0. So put v is equals to 0. This will become 2f x max divided by m minus, or you can take it on right side. It will become k x max ka square divided by m. M and m will cancel out. And this will be, x will cancel out one power. So x max you will have as 2 times of f by k. ठीक है. Got it? And if you will compare that at equilibrium, the extension is this f by k, and at maximum extension it is just doubled. So x max is 2 times of x equilibrium. So I hope you are clear with this question. If you have any kind of doubt, you can write it in the chat box. Okay. Now this question, it is a very simple question, and I have included this question because of the air resistance factor, the work done by a resistive force. So try to solve this question. You have 30 seconds to solve this question. So body of mass m is dropped from a height h. The speed with which body hits the ground is 0.9 square root of 0.9 gh. Now find the work done by air resistance. Okay. So let's say this is the ground we have. This is the block, which is ball, which is moving a body. We have considered it a ball of mass m. So a force of mg is acting in downward direction, and as it is moving down, so a air resistance will act in opposite direction. The air friction, I will say. Okay. And let's say it is dropped from a height h. So this is h. Since it is being dropped, so the initial velocity is 0. Now at finally, when it hit the ground, the velocity has 0.9 gh. So here the conservative force mg is acting, but a non-conservative force, which is air friction, is acting. So we cannot apply the conservation of mechanical energy here. So what can we do? We can apply the work energy theorem. So by work energy theorem. So by work energy theorem, we can say that work done by mg force, because only two forces are acting, and work done by friction is equals to change in kinetic energy 1 by 2 times mv final का square minus 1 by 2 times mv initial का square. Initial velocity is 0 because it is just dropped, so it will become 0. This term will become 0. And final velocity is given to us, which is 0.9 times gh, square root of. Now, the work done by this mg force, since the displacement is in the direction of this mg, so we can take it as mg dot h. Okay, and it will be a positive value, plus work done by frictional force. This is what we have to calculate. Now 1 by 2 times m, what is the value of v final? It is 0.9 times GH. This square has just vanished this square root term. Now, work done by friction is equals to 1 by 2 times 0.9 mgh minus mgh. You will cancel it. It will become 0.45. And finally, you will have the value of work done by friction as minus 0.55 mgh. This minus sign indicates that the work done is negative, which means the force is acting opposite to the displacement. And you can see in the figure also. Okay? So I don't think that you have any kind of doubt in this question. This is a very simple question. So if you have any kind of doubt, you can ask. Now move on to the next question. Yeah. So this is an important question. The kinetic energy of a particle moving along a circle of radius capital R depends on the distance covered as k is equals to alpha s square. So this is the relation between kinetic energy and displacement. Now where alpha is a constant, so find the force acting on the particle as a function of s. Okay. So I'm giving you 1 minute to solve this question. Try to solve this question. Okay. Just give me 10 seconds. Huh? Sorry for the disturbance. Just keep solving this question. So anyone of you try to solve this question? Are you trying to solve this question? Adi is here, JNV, Anand, Kolhapur, Bhavnagar, Ramnagar. Any one of you are trying to solve this question or not? So that I will not give you 1 minute. I will utilize this for to solve this question. Okay. There is no problem in screen visibility and voice now. Please make sure of that. So in this question, a relation is being given between the kinetic energy and the distance covered. Okay. And that relation is k is equals to alpha s square. We know that kinetic energy is given by 1 by 2 times mv square is equals to, it will equals to alpha a square. So this is equation number 1. Now, this is the question of circular motion. Okay. And we have to find the dependency of force as a function of s. Okay. We know that in circular motion, there are two forces acting, which is Fc, the centripetal force, and Ft, the tangential force. We know that Fc is equals to mv square upon r, because here capital R is given as the radius of this circle. So Fc will become mv square by capital R. What about Ft? Ft is equals to mass into tangential acceleration. We also know that. This is equation number 2. These both. Okay. Now, you can put the value of v square to get the relation between Fc and S from this equation. So Fc here is m. What is the value of v square? You have to divide, you have to take this m by 2 term here, so it will become 2 by m. So you 2 alpha s square by m you have, and divided by r. This m and m will cancel out, then Fc will become 2 alpha s square upon. This is equation number 3. Now we know that this 1 by 2 times mv square is equals to alpha s square, or we can say this v square is equals to 2 alpha s divided by m. 2 alpha s square by m. Now we need at. This is the tangential acceleration, and this velocity is nothing but the tangential velocity, the linear velocity. So what do? We differentiate this velocity with respect to time. So what do you have? You will have 2v, because v square is 2v, and then again v, dv by dt is equals to 2 alpha and capital M are constant. So we can take them out, into 2s ds by dt. Okay. Now this ds by dt will become v. The change of position with respect to time is velocity or speed. This v will cancel out this v, and this 2 will cancel out this 2. So dv by dt is equals to, what do we left with? 2 alpha s by m. Okay. This dv by dt is nothing but acceleration. So you have 2 alpha s by m, which is 18. Now put the value of 80 in this second equation. So ft you will have as mass into tangential acceleration, which is 2 alpha s by m. M and m will cancel out. So ft you will have as 2 alpha s. Now the net force on the system, since these forces are perpendicular to each other, having an angle 90 degree in between them, so the resultant of them will be Fc square plus Ft square ka square root. Put the values. Fc square is 2 alpha s square by capital R, plus it will become 2 alpha s by m whole square. You can take this 2 alpha and s as common. So you are left with, from this 2 alpha has been come s square. It will become s raised to the power 4, and s square we have taken out from the square root. So it will become s. So here you have s square by r plus, and from this 2 alpha s we have taken out. So it is 1 by m square. So this is the relation between force and the displacement, or the position of the particle. Okay. So I hope you are clear with this. If you have any kind of doubt, you can ask. So is this clear to you, each and every one of you? Is this question is clear to you? Write this thing in the chat box now, if this is clear to you or not. Okay. So now, next question. So a block of mass m1 is resting on a smooth horizontal surface. A massless spring of stiffness k is attached to the block as shown. This block is, let's say, m. This block is m2. This block is m, because m1 is resting on a smooth horizontal surface, and a massless spring of stiffness k is attached to the block as shown. m1 block के साथ this stiffness k का spring attached है. Another block of mass m2 is moving with the speed u. This block is moving with the speed u towards the stationary block, इस block के पास. Now we have to find the maximum compression in the spring, and all the surfaces are, this horizontal surface is also smooth. So this is a smooth surface, not a rough. Okay. Now this is not a simple type of question, because you don't say कि when this M2 black block will strike it, then the spring will start compressing and M1 is resting. No, when it start compressing, the M1 will also start moving, because a equal and opposite reaction is acting on the M1 also by the spring, है ना? So in this question, both the blocks are moving. So we have to take a relative frame of reference. Okay. And this question I have select because in this question, the work done by pseudo force come into contest. Okay. So pseudo force is a kind of conceptual thing which is being asked in this question. Okay. We are going to use this. So this M1 block, initially what will happen when this M2 block, this is M2, and it will strike this spring just at the start, and now it is moving with speed u. Now at some instant after, it has compressed this spring and its velocity will become v, let's say from v to u. Now this spring is compressed, so it just want to extend, so it just want to open its arm which is attached to M1 and M2. So it will apply a equal and opposite force on both the side, which is kx. Let's say the extension or the compression in the spring is x at this point of time. So because of this kx, or because of this spring force applied by this end on M1, M1 will also start moving with some acceleration, because there is a force, so there will be an acceleration. So this question will become very complicated if you try to solve it from the ground frame of reference. So we are going to solve it with a non-inertial frame of reference. How? Okay. So let me tell you. Now we have set an observer on M1. Okay. Now in any situation, the M1 will become stationary to this observer. To this observer. The M1 will always be in the M1 will always be in equilibrium, or in always in rest, because the observer standing on this. So this appears to this observer that the M1 block is not moving at all. Okay. So initially what will happen to this observer, this block will appear to this observer, like say this is the observer here on this block. So initially, and this is the spring. So initially this block coming closer to this observer, and it will appear to this observer also कि ये block मेरे पास आ रहा है with a speed of, when it strike this, also from the ground frame of reference, this block start moving. But for this observer, the block is not moving. Only this block is moving. So at another situation, this is the observer here. This block has also start moving, but for this observer, this block is not moving, which means M1 is not moving, only this block. And this has reducing velocity now, because the force is acting on this block by spring. Now the velocity is reduced by V. Okay. At some situation, at a particular instant, what will happen? This velocity V This velocity v is nothing but the velocity observed by this observer. So this velocity v is the relative velocity. Relative velocity. Okay. So we can say that when this relative velocity becomes zero, because ये ब्लॉक आता जा रहा है आता जा रहा है, दिस इज द m1, ये भी चल रहा है ये भी चल रहा है, अब ये आता जा रहा है एट दिस पॉइंट, व्हेन द रिलेटिव वेलोसिटी जो इस पे ऑब्जर्वर बैठा है उसे जब इसकी वेलोसिटी विल अपीयर टू बी जीरो, एट दैट मोमेंट द स्प्रिंग हैज इट्स मैक्सिमम कंप्रेशन, बिकॉज उसके बाद क्या होगा, दिस ब्लॉक विल मूविंग स्टार्ट बैकवर्ड because the spring force has extended. ठीक है, is dominating in that case. Got it? So for maximum compression in the spring, you must say that कि when the relative speed of this block m2 becomes zero with respect to m1, then we can say the spring and its maximum extension, maximum compression. ठीक है? I hope you got the concept of it. Now let's say initially the after the after this block hit this m1 block, this m2 block has a velocity v, and now this m1 velocity has acquired m1 has acquired some acceleration which is a1. Okay, got it? And this is the force acting on it. Sorry, not in this direction. This force is acting in this direction because spring is compressed. Okay, so this force kx is acting on this block m. So what you can say that F is equals to ma for second block for m1 block. So F here is equals to kx, which is equals to m1 a1. Okay, so you can say that a1 here is kx over m1. So this is equation number 1. Now if I talk about block m2, if I talk about block m2, this is m2. Now spring force is acting in this direction, so I am taking this direction to be the left of it. This is the direction of spring force, which is kx. Now the relative motion we are seeing, okay, by this observer, but this observer had some acceleration a1, so this will become a non-inertial frame. So if we want to apply the Newton's law in non-inertial frame, what I have told you in the question discussion of laws of motion, we have to apply a pseudo force on the particle which is moving in this frame, and which is we are observing in that frame, and we are observing this block m2, so there must be a pseudo force acting on this block m2, okay, which is opposite in the direction of motion of frame. So frame is moving in this direction, so pseudo force will act in the opposite to that, which means the pseudo force will also act in this direction, which is equals to the mass of the system multiplied by the acceleration of inertial acceleration of the frame of reference. So frame of reference means m1 block is moving with a speed of moving with an acceleration of a1. So this force, which is pseudo force fs fp, is equals to m2a1, and this block is M2. Got it? Now you can say that the net force on m2 is equals to kx plus m2 A1. You can put the value of A1 here, which is equals to Kx plus M2 into Kx by M1. This is equation number 1. We have put the value. Now you can take Kx as common. So you will have M1 plus M2 divided by M. So this is the net force acting on this system, on this block M2. ठीक है? Now, in the case of maximum compression, what will happen? The velocity of block with respect to velocity of block M2 with respect to M1 will become 0. So you can say that at maximum extension, at maximum extension, the velocity or the speed, let's say the speed of block M1 with respect to M2 will become 0. ठीक है? Means that V will become 0. ठीक है? So try to now. If you have any kind of doubt in this situation, you can ask. Okay, you can take a look of it and just give me 10 seconds. Okay. Sorry for the disturbance. Now, so what we have discussed that we have calculated the net value of force, which is F acting on this block M2. And now we have a concept that for maximum extension, the speed of the block M1 with respect to M2 will become 0. Now apply, let me just change the color of pen. Apply work energy theorem. Work energy theorem we are applying here for block M2. For M. So this is M2. Initially, it has a velocity U, and final case mein it has a velocity V. Okay. So we can say that work done net is equals to change in kinetic energy. Now, work done is given by the net force, which is capital F acting on it. So you can say that F dot dx. But the displacement is in opposite direction because this block is moving in this direction and the force is acting in this direction. So this F dx integration delta k. So this F dx will open as F dx cos 180. It will become minus F dx is equals to delta k. So m by 1 by 2 mv final. V final is v square minus 1 by 2 mv initial, which is u square. Now you can put the value of F, which is kx into m1 plus m2 by m1. So m1 plus m2 by m1 into kx dx is equals to 1 by 2 times mv square minus 1 by 2 times mu square. Now, we are we are compressing the spring from 0 to x max. ठीक है? 0 to x max. Now, when this limit is 0, nothing will happen. But when this x max has been reached, so you can say that this v will become 0, which is the relative velocity. Okay? And this is a minus. So you can say that minus of m1 plus m2 by m1 integration of kx dx will become 1 by 2 times kx square. And this x is nothing but x max is equals to minus of 1 by 2 times mu square. M, no, you cannot cancel this m. This is m2, m2 all the time. Okay, m2. Okay, so here you can cancel out this minus term from both the sides. So what you will have? You will have m1 plus m2 by m1 to m1 into kx max whole square, x max square is equals to 1 by 2 times m2 into u square. 2 and 2 will also cancel out. So x max here is, this term will go in this direction. So it will become m1 m2 by m1 plus m2 into u square by k. So x max is nothing but square root of m1 m2 divided by k times m1 plus m2 into u. So this is the expression for maximum extension in the spring. Okay. So if you have any kind of doubt, you can ask. Otherwise, the lecture is being over for you guys. Thank you so much for being attentive. If you have any kind of doubt, you can ask. Huh?